Continuing on with our Module 11 CYU, on number 3, we're asked to algebraically prove the following identities. And so we pick one of the expressions and we simplify it till it matches the other one. This is basically what we did on number 1. We just, on number 1, we had to sort of pair them up with graphs first. I tend to like to pick the side that is more complicated looking when I choose it, but sometimes we'll see a few where you don't really know which side's more complicated looking, and then you really just can pick. On this one, I would say it's the left side here, because I got a cosine and a sine. Now, it's really tempting to think cosine squared theta, sine squared theta, it's a Pythagorean identity, I'm done. But it's not, because that's 2 cosine squared theta, but it's not a 2 sine squared theta, so I can't just use a Pythagorean identity here. But I can replace sine squared theta. So remember, we talked about in one of the earlier problems that 1 minus cosine squared theta was equal to sine squared theta. So 1 minus cosine squared theta is equal to sine squared theta. And that's a version of, that's a rewritten form of sine squared theta plus cosine squared theta equals 1. You should write down this other version. You use it a lot. It's similar to the 1 minus sine squared theta. So if you don't have those versions written on your identity sheet, I might add them. All right, so we're going to replace that sine squared theta with 1 minus cosine squared theta. And I always like to put what I substitute into parentheses just to make sure we're clear in case I need to distribute anything. In this case, I don't need to, but just to be on the safe side. Equals, and I'm not going to do anything to that right side. Well, I have 2 cosine thetas, and I'm minusing 1 cosine squared theta. This is no different, and I'm just sort of going to put a little note down here. If I had 2x squared plus 1 minus x squared, think about combining like terms here. If I had a 2x squared minus x squared, that's really just 1x squared. And so I can treat the cosine squared thetas the same way. It's just like a variable. So I have 2 cosine squared theta minus cosine squared theta, which is just equal to cosine squared theta. And I still have that plus 1. Now a little bit of commutative property and flip the order so that it matches the 1 plus cosine squared theta. All right, letter B. I think it's very clear which one is the more complicated side. That would be the right side. So we got some identities down here at the bottom. So before we replace with sine and cosine, we're going to deal with those. So sine of pi over 2 minus x is just sort of the shifting of our function, is actually just equal to cosine of x. And then tangent of negative x is equal to negative tangent of x. So let's replace those. So we have still cotangent of x and cosine of x in our numerator. But down below now we have cosine of x and then negative tangent of x. Next up, let's replace all our sines and cosines. Now I'm going to move the negative to the front. I do know that my final answer does need to be negative, so that's helpful. Cotangent of x is equal to cosine of x over sine of x. And then I have times cosine of x. And then on the denominator here, I have another cosine of x. And that's going to be times sine of x over cosine of x. Well, I got a cosine and a cosine, and they are being divided. So I'm going to simplify those out to 1, just to make my life a little easier. Dividing by a fraction is the same thing as multiplying by a reciprocal. So let's write that out. So we have negative cosine of x over sine of x times the reciprocal of sine over cosine would be cosine of x over sine of x. Well, cosine times cosine is cosine squared x over sine squared x. Oops, and I dropped off the negative. Cosine over sine. You could also think about this. This is just sort of a side note. You don't need to write it out this way. But if it helps you visualize what we're about to do, that whole fraction is being squared since both pieces are being squared. Well, cosine over sine is the same thing as cotangent, and it's being squared, which is exactly what we're looking for. Yay, negative cotangent squared x. We did it. Success. All right, this next one is one where you might look at it and go, I don't know what side I need to simplify. They both look weird. Well, I'm going to go with the addition side. I find that combining things through addition might work out a little easier. So here I got tangent and cotangent. Well, tangent is sine of theta over cosine of theta, plus cotangent, which is cosine of theta over sine of theta. And we talked about this on some earlier problems. We want to get those common denominators. So we're going to multiply here by cosine of theta over cosine of theta, and over here by sine of theta, so that I can get a single denominator of sine theta cosine theta. And then notice on the top I got sine of theta times sine of theta, which is sine squared theta, and cosine of theta times cosine of theta, which is cosine squared theta. And you might have alarm bells going off in your head because this is our Pythagorean identity equal to 1. So notice that sort of advantage of simplifying out some fractions. Well, this, with the two values being multiplied in the denominator, I could split it back into two separate fractions being multiplied. One would be 1 over sine, and one would be 1 over cosine. And you might be going, why would I do that? Well, 1 over sine is cosecant theta, and 1 over cosine is secant theta, which happens to be exactly what we were looking for. Ta-da! Check, we did it. So combining a few fractions, simplifying it down, and we get what we were looking for. All right, obviously I'd say the left side is where we want to start. And just like we did on the previous problem, we are going to combine some fractions. So in this case, secant is 1 over cosine of x. And I am going to write that out because when I go to make my common denominators here, I'm going to multiply this side by sine of x over sine of x, and this by cosine of x over cosine of x. And the advantage of having written out that sort of secant as 1 over cosine is, notice right here, cosine of x times 1 over cosine of x is just going to be equal to 1. So I actually have 1 over cosine of x sine of x minus sine of x times sine of x is sine squared x. Alarm bells going off in your head. Let's recognize that Pythagorean identity, which should be equal to cosine squared x all over cosine of x times sine of x. We can simplify a little because we got 2 cosines being multiplied in the numerator, 1 in the denominator, so we are really left with just cosine of x over sine of x, which is equal to cotangent of x, which is what we were looking for. And the nice thing about identities is you know where you need to end up. You just need to use some algebra skills to get you there. All right, we got 2 more identities. On this first one, again, I'm going to deal with the left side. Looks a little more complicated. I got a double angle going on. And I really don't know, with the double angle with cosine, there are 3 different forms. I noticed in the denominator, I got a cosine and a sine. So I think I'm going to go with the form that involves both, which is, cosine, just so you know, of 2t would be equal to cosine squared t minus sine squared t. And so I'm going to replace this with our sort of alternative version. Now, that is a difference of squares, which means I can factor it. That would be the same thing as cosine of t minus sine of t, and then cosine of t plus sine of t, all over cosine of t plus sine of t. And so, I shifted pages when I didn't mean to. We got some reducing going on here because we got the same factor in the top and the bottom. So then we're left with just cosine of t minus sine of t, which is exactly what we were looking for. All right, last but not least. This is one of our double angle identities. It is equivalent to cosine of 2 theta. Just straight up double angle identity. This one's a little different. Now, I like to sort of think about it as 2 times 2 sine theta cosine theta. Because if I think about it this way, then I notice that that 2 sine cosine theta is actually sine of 2 theta. It's the double angle for sine. And the reason then is I now have another version of my sine double angle identity, but instead of just a theta in there, I have 2 theta. So what ends up happening is you end up with sine of 2 times 2 theta, which would be sine of 4 theta, which again, surprise, surprise, is what we were looking for.